The coral reef, the most biologically diverse marine habitat in the world, hosts to an extraordinary variety of plant and animal, becoming their significant feeding, nursery, and breeding ground. Offering countless of benefits to mankind, millions of people depend on intact reef for various socio-economic and ecological values. Yet, they are also one of the world's most fragile and endangered ecosystems. Around the world, they are rapidly being degraded naturally from climate change, in which, ironically and anthropogenically from human activity itself, that excessively release greenhouse gases. Consequently, coral reefs are facing ecological collapse, where an estimated 70 to 90% of coral reefs could disappear by 2050 if emissions are not curbed. Because of that, considering their significance, they are deliberately destroyed with human activity, reefs may be unable to recover naturally. And here, active restoration can be used to rehabilitate the degraded reef, where the remote sensing can progressively help the ocean.
Assalamualaikum and hi everyone. I am Abdul Zepri and welcome to my channel. Today, we'll talk about the application of remote sensing in coral restoration. The term of coral restoration, which also can be known as coral gardening, was pioneered in 1990s and involved the collection and culture of coral fragments and the transplantation of those fragments onto the reef. And basically, in reef restoration, there are several clear objectives. And to achieve all these objectives, it depends on the survivability of the transplanted fragment, in which this survivability depends on where the nursery grown coral fragments are transplanted. This is where the remote sensing play a key system as a more methodical way to identify which reef location are worth restoring and have a highest chance of surviving projected climate change. So, first of all, what is remote sensing? Basically, remote sensing is the term widely applied for the acquisition of the information about the land, sea, and atmosphere by sensor located at some distance from the target of study. For coral reef, since they are largely occur in clear shallow water, many reefs highly visible when observed from above the ocean surface, and thus make them highly amenable to being mapped and monitored using remote sensing. In terms of field-based monitoring of coral reefs, it is known to be costly, time-consuming, and geographically limited. Because of that, remote sensing is likely the only technology enabled to measure coral reef pressure from anthropogenic stressor in a less time and also at scale sufficiently large enough to capture the habitat change over time. Basically, there is a broad suite of remote sensing technology and sensor exists, which can be used in assessing the coral. This sensor can be deployed on various platforms, either shipborne, airborne, spaceborne, or even underwater platforms such as AUV. And generally, for the finest resolution of less than 0.1 meter, all these sensors can be mounted either on the boat base, remotely operated vehicle, or low-flying aircraft, either manned or unmanned aerial vehicles. In terms of the technique used for the sensing, basically they can be categorized into either passive or active remote sensing. In coral application, passive remote sensing, which rely on the reflected sunlight or emitted heat, can include photographic, multispectral, hyperspectral, and infrared imaging. Meanwhile, for the active remote sensing, which record a return signal from emitted source, can include laser, radar, and other radio-based scanning approach. So now, let's look back on how all this remote sensing technology and sensor can be applied to informing coral reef transplantation and restoration success. So basically, as said before, even the best reef transplantation design will result in failure if it was done in a poor location. This is because site selection is the key to successful restoration. The use of remote sensing can optimize the process of determining the best site to transplant by providing complete aerial coverage of reef system and assessment of multiple criteria of parameters considered to be key successful restoration. There are several criteria considered by reef restoration practitioners for the coral transplantation, or specifically when choosing which reef system to restore and which area within that chosen reef to be transplanted, where most of these criteria are able to be remotely sensed. So, the first key criteria of coral restoration that can be remotely sensed is the general distribution of reef geomorphology and benthic cover, in which of the remote sensing technology available today, satellite-based multispectral technology is the most mature, test, and suited for this criteria determination, as it helps in site selection by identifying which reef to restore through classification of the size and extent of the coral reef. After deciding which reef to restore, the area within the reef that best suited for transplantation must be identified, in which spatial resolution finer than most satellite-based sensor is needed in order to provide detailed site characteristics relevant for transplantation. For this, airborne hyperspectral remote sensing, or also known as imaging spectroscopy, is at the technology forefront of optical sensing, providing the most detailed benthic habitat map, successfully classifying benthos into bottom types such as fleshy algae, turf algae, seagrass, and coral rubber. The next criteria is the water depth, in which airborne laser scanners such as LiDAR are currently the best demonstrated technology for providing the detailed reef bathymetry and rigidity for water depth less than 50 meter at a resolution around 5 meter or closer within a survey area that are less than 100 km square. This measurement also allow detection of spurs and grooves that are good for site selection as they are reduced predator migration. The fourth criteria is the important biophysical properties of the water, which can be measured by airborne radiometer and radar sensor, where pollution, algal blooms, and turbidity, all of which are important restoration consideration, can be inferred from the measured variable, providing essential water quality parameters. Next, another important restoration criteria includes sea surface temperature. They are greatly associated with coral bleaching. This criteria can be studied using thermal sensor on various platforms. In addition, the presence and abundance of herbivore fish such as parrotfish as well as predators such as sea otter also act as important criteria in coral restoration, where this criteria can be provided by acoustic sensing such as by sonar sensor that enable to provide measurement in both the shallowest and deepest environment of more than 100 meter depth and relatively insensitive to turbid water. Lastly, photographic sensor in remote sensing platform currently the best suited technology to assess the next criteria, which is the taxonomic composition. And basically, it requires a board-based platform to provide information at the resolution need for restoration. This technology also allows detection of space competitors such as encrusted sponge. In addition, after the transplantation is done, maintenance and monitoring can represent the biggest cost for the practitioner, where transplants are susceptible to the dislodgement, storm damage, disease, bleaching, and also predation. Because of that, there are 6 ecological benchmarks of factors recommended for evaluating coral restoration success, where most of these factors can also be remotely sensed, similarly to the technique and technology of remote sensing explained before. So, in conclusion, remote sensing can provide a powerful avenue to help achieve reef restoration objective. While this remote sensing may not provide the fine-level detail of in-situ field survey, it can reveal both large and small-scale patterns, thus eventually reducing the need for the costly and timely in-water survey. So, that's all for today's video. Don't forget to like and subscribe, and see you again. Bye!